In this series of videos, I'm attempting to repair and restore an Osborne OCC1 vintage computer. So far in this series, I've stripped the unit down and started cleaning it up, gone through the power supply, and I'm now working my way through the various sub-assemblies. My normal approach when I repair something like this is to go through all the sub-assemblies, fully test them, put them back onto the unit, and by the time I've got all the sub-assemblies tested and the unit reassembled, it quite frequently just works. I'll then have to maybe sometimes mop up a few remaining faults, but I realise that doesn't necessarily make for the most interesting videos. So what I'm going to do this time is plug it all back together and see what it does. However, before I do that, I will tidy up the two disk drives, simply because if you try powering these up and running them, you'll either damage your disks or you could damage the drive or the drive belt or something. So I will go through these first. It's not to say they'll end up necessarily working, but at least if I go through them mechanically, I've got a better chance of them not damaging themselves. So this is one of them. You can see there is a lot of corrosion on this. It's mostly aluminium, so I think this has been stored somewhere damp, and I do need to clean all this off before I try to run these. So that's the first unit. The second one I've already started to dismantle. They're quite easy to get apart, just a few screws holding the screen on them. You can then take out a couple of screws, disconnect 4 plugs, and you can then get the board out. And this actually looks in quite good condition. It doesn't appear to be damaged. The two drives are identical. The only real difference is that the drive at the end of the cable has a termination resistor, whereas the other one doesn't. So that's the only real difference. These are type 51 drives, although they don't have a typical back side to the connector. Quite often you'll find that all these are connected together on the bottom side of the board. On this one they're not. They're actually the power connections for the drive. But other than that, it is a typical type 51 drive. So that's the control board. I don't know if it works. The next thing is to look at it mechanically and see if we'll see if the head moves. Okay, that's a bit too tight. I'm not going to force it. It is making some strange noises. Okay, that's extremely stiff as well. It is turning, but it's very tight. Looking on the underside. Okay, that is also extremely tight. So let's get the belt off and see if it's actually the motor or the spindle that's tight. So this should spin around freely. It's actually getting freer as I'm turning it. So what I shall probably do is just pull the bearings out, rinse them out, re-lubricate them. They're not making any noise, so I think that it's just the grease has started to go hard. The motor seems to spin okay, but again I will lubricate the bearings on that. The other thing I will do is take out the guide rails for the read-write head. The way I do this, there's a bracket on the back. You can take out this screw that's in the center, and then you can slide the guide rails out. I do them one at a time so I don't lose. What I don't want to happen is for the registration for the stepper, which is this positions the head. I don't want to lose the registration for that, so I'll take the guides out one at a time, polish them up, put them back, lubricate them, and then hopefully this will start to move a bit more freely. As I say, at the moment it's not moving well at all. I'll also try and get rid of the corrosion. You can see there's a lot of white corrosion on this housing, on the chassis, so again I will try and clean that up. I'll clean up the plastic. This is also a bit tight, so that needs a bit of attention as well. But other than that, it doesn't seem too bad. It just seems to need cleaning and lubricating, so I'll do that with both drives. I won't show that on the video. It'll take a couple of hours, and it's just really going through them, cleaning them, bit of lubrication, and then they should be ready to test. I'll then plug the entire unit back together, we'll power it up and see what it does. That's the two drives cleaned up. I've cleaned the guides, re-lubricated it where it needs it, got rid of the corrosion, cleaned up all the plastic parts. I did do some basic testing on the board, the usual static testing I do with a multimeter looking for shorts. Couldn't find anything. I do have a floppy drive tester that I've shown in previous videos, but I won't use it this time. We'll just try booting the machine up and see what happens. So everything now spins freely, no weird noises. The bearings aren't perfect, they will rumble a bit, but they're not bad enough to warrant changing at this point. I may change them in the future if the machine comes back to life. The heads move nice and freely now, without making the horrendous screeching noise that they made before. So I'll get these refitted to the chassis. I will then fit the main board, get it all connected up, and we'll power it up and see what it actually does. I've refitted the two drives to the chassis and I've got them connected up. I've got them connected to the main board, which is behind the unit. You probably can't see most of it, but everything's connected up. I've plugged the keyboard in, and this is upside down of course, so if anything comes on to the display it will be inverted. And what we had before was an overbright, badly distorted display, and we got a startup beep and we got what appeared to be the startup screen. It was quite hard to read, so we'll see what happens this time. We'll see if I've broken it, and the only thing I've really done to this so far, apart from clean the drives, is to replace some caps on the power supply. So I'll power this up. We got the startup beeps, that's quite a good sign. And the display has come on. It is upside down, but it is giving us the correct startup screen. It's asking us to insert the boot disk into drive A, which in this case is this drive. I have got a disk in there. It's not a boot disk, but the system won't know that until it tries to read it, and it's telling us to press return to try and boot. So I'll press the return key. Now this is being very optimistic. These keyboards are fairly notorious for not working, but we'll try this anyway. And as expected, we're getting nothing at all. It's not even trying to access the drive, so it's not because it's the wrong disk. It could be a faulty drive, of course, but I would expect to see some change on the display. I suspect that the keyboard's not working, so what I'm going to do is unplug the keyboard, and we'll put a jumper on the connections to the keyboard. If we have a quick look at the schematic. Okay, so this is the part of the schematic for the interface to the keyboard. I've just written the numbers down here because they're not very clear on the schematic. These are the pin numbers for the connector that the keyboard plugs into. That's P4. That's the connector on the main board. And it's a very simple keyboard. There's nothing active in the keyboard. It's just switches, and it's just a simple matrix. So we have the rows at the top here that are driven by the main unit, and then the columns are red. And depending on which column is seen as active, depending on which row is currently active, the system can figure out which key is pressed. And there's a table in the technical documents that show you which is which. So these are the possible key combinations. Down here we have the pin numbers for the connector, so that's these numbers here. And if you just look down the table, you'll see that for return, the pins we're interested in are pin 3 and pin 15. So that is row 0, column 5. So if I short these two pins together on the connector on the board, the system should think that the return key is being pressed. And if the main board is actually working, then that should at least try and read the floppy disk or do something and come up with an error message of some sort. So I'll power the unit off, get the keyboard unplugged, we'll tip the main board onto its end, and I'll get a jumper ready so that we can try to fool the unit into thinking that a key's being pressed. I've got a jumper in place of the keyboard. I don't think this is going to work simply because I tried putting a meter across the two connections coming from the keyboard, and I am seeing continuity when the return key is pressed, so it looks like the keyboard itself is working. I've got a feeling this might be a fault on the main board, but we'll try this anyway and see what it does. So we'll power it back up. Okay, so it's come back on. One end of the jumper is on pin 3, so all I need to do is to try and connect the other end to pin 15, and that should cause the unit to start up, and that's this connection. So we can see the display is flickering, but it's not making any attempt to do anything else. So looks like we do have a fault on the main board, or we have a faulty floppy drive. So it's time to start investigating the electronics. We finally have some electronics to do some fault finding on, and we'll start with the keyboard interface. It looks like this might be working, but one problem we could have is it could be that some of the other lines are not working, so it might think a key is permanently held down. Normally the display flickers if it does that, and it's not all the time, and it's not doing that, but it kind of depends which key is being held down, and it might be that that's fooling it into thinking the wrong key is being pressed. But either way, we can figure this out using a scope. We'll see which of the column and row lines are active, and make sure that the IC is being strobed, and we'll go from there. So I'll spin all this around. You won't be able to see everything at the same time, unfortunately. This is a bit of an ungainly contrivance when it's out like this, and it's very difficult to show everything. But what I'm going to do is I'm going to flip the main board back the way up it would normally sit, and then we can access the back side of the board, and we'll be able to access the pins on this IC and on this IC, and we'll try and get some idea as to what's going on. I've got the board flipped back up the other way, and what we'll do now is check to see if we're getting the expected signals on the various lines. So we'll start off looking at this pair of ICs. There's two ICs providing these buffers, and these are the ones that feed the row output signals to the keyboard. Bit of a complication here in that these are open collector drivers, so they won't actually give a signal. If you just unplug the keyboard, you won't get anything meaningful out of these, because there'll be nothing pulling up the line. But that in itself is a good indication as to whether they appear to be working or not. What you can do is just temporarily hook a resistor to the output. Now normally when you press a key, this line is pulled high because it will go through the keyboard, through one of the keys, and then these pull-up resistors will pull the line high. So it doesn't just pull this line high, it also pulls the input line high as well, and that allows these to be multiplexed. But what we'll do is we'll start off with this IC. So it's designated as UE14, so U is just means an IC, and then E14 is row E IC14. So the board's upside down, of course, and row A is the one furthest from us. 5 rows A, B, C, D and E, so E is the one closest to us, and the ICs are numbered starting from our right. As I said, this is upside down, it would normally be numbered from the left. So this IC here, this 20-pin IC, is this one, UE12, and so UE14 will be 2 more ICs along, so it will actually be this one here. So that's the one we want to start looking at, and we want to look at pins 11 and 10. 11 is an input, 10 is an output, and we'll see if we're getting any signals there. So we'll start off, and again the top of the IC is furthest from us, so pin 1 is this one, and we want pin 11, which is this one, and this should be a regular signal. It looks a bit messy on the scope because it is of course an address line, and it's only meaningful in the context of the keyboard when the system is explicitly trying to access the keyboard. But the fact that there's data there means that at least there is some signal going to that IC. Doesn't mean it's the right signal, but at least there's something going there. What we can now do is look at pin 10. This is the output. Now at the moment there's nothing there because, as I said, it's an open collector signal. What we can do is just temporarily hook a resistor to that, and you can now see that we are indeed getting a signal on the scope. So I'll do that for the rest of the buffers, and we'll make sure that they're all working, and if they are, we'll move on to the input reading IC. Okay, well the buffers all seem to be working for the road drivers, so what we'll do now is we'll come back and look at the inputs and see if this IC is working. So as I said, this is UE12, which is this 20 pin IC here, and we'll start off looking at pins 4 and 5. I think it says 4 and 5, very hard to read on this diagram, and we should be getting a signal coming here when a key is pressed that drives this high at the right time, and that should also be visible on the output. And again, this will only be valid when this IC is enabled, when the system's trying to actually read the keyboard. So what we'll do to start with is look at pins 1 and 19, and in theory we should be seeing a strobe on here that indicates that the system is at least trying to read the keyboard. This is pin 1, active low by the way, so that's looking good. And then pin 19, again, if you look at pin 19, it's actually derived from here, so it's a read line, so it will be quite active, but again it's only valid here when it's in conjunction with the signal on pin 1. So pin 1 is going to be the one that determines where in the overall scheme of things the keyboard is being read. We're getting a signal there, so that's quite promising. So now we'll look at pin 4. So we've got our jumper on pin 3, and if we look at pin 4, that's coming from pin 10 on the connector. So we'll put the scope probe on pin 4, 1, 2, 3, 4, which is that. Okay, so that's pin 4. If we now jumper that to pin 10, and pin 10 is the this will effectively connect the row 1 strobe to this input. If it's working, we should see a signal appear on the scope, which we do. So we're now getting the signal. This is effectively the same as pressing one of the keys, and we can now look at the output of the buffer. So we're looking at pin 4. We need to look at pin 5, and we are getting some output, but let's see if that disappears when we disconnect it. Now it doesn't, because what we're looking at here, if you look back at the schematic, is that is data 0 line, so it's very busy doing other things. So what we need to do here is connect up at least 2 separate lines, one to pin 1, which will give us the strobe when it tries to read the keyboard, and the other one is what is this IC doing at that point. Otherwise we're just looking at the data line that's doing all sorts of things in the background in the rest of the system. Okay, so what I would normally do here is connect up the logic analyzer, but because there's a daughter board sitting on the top of this main board, we can't easily get access to the other side of this board at this point. So what I'm going to do instead is get a second probe on the scope, and we'll use that to trigger the scope and see if we can manage to capture some valid data when we have effectively a key pressed. So I've got a second probe attached to the scope. If I now put one probe on pin 1, so that's our strobe going to the buffer IC, and if we look at pin 5, which is the output of that IC, we can see that there is some data on there. I'll just try and get this configured so I can hold it with one hand. Okay, now if you look at the scope, you can see that there is a signal here at the same time. There's a lot of noise on here as well because it is doing other things, but you can see that there is a low signal here when this strobe occurs. If I now remove the jumper, that disappears. Put it back, and so you can see that there is data coming out of that IC at the point of the strobe. This is one of the second strobe line, by the way, going into the IC, so it can distinguish between different time events on the machine. But there is definitely data going out of that pin when I short this line. So I can now do the same thing for the other lines. So that was testing this pin here, so that pin is responding and going low when I effectively jumper this pin down to this pin. And we can do the same thing now with the other ones. I'll use the same strobe line and test the other 7 outputs, and we'll see if they all work. So I thought I'd show this one because it does make it a little bit clearer as to what's going on. So the yellow strobe line is going low. You can see on the blue line at that point there is a low signal. If I now remove the jumper, this is the same as releasing the key. Notice that signal disappears. If I put it back, the signal reappears. So that's all I'm doing. I'm just going through and checking that the signal appears at the right time to show that the system can actually see the keys being pressed. I've checked all the column buffer output lines and they're all working fine. Also, none of them are tied low all the time, so it appears that they are all doing what they're supposed to. The one we're looking at the moment is actually jumpering between row 0 and column 5, and that is the return key. So if I effectively jumper what should be the return key, you can see that the line goes low at the strobe point, and so that is indicating that the system, as far as the input or the output from this IC, is seeing the key press. So it's not that that's at fault. So it looks like the issue we have is somewhere else. So it could be a faulty drive, it could be anywhere else in the system. So it should now be quite interesting trying to track this fault down, and we'll save that for the next video. But this should now be quite an interesting fault finding exercise. The board input buffer from the keyboard is seeing the correct key press, but there's absolutely nothing happening on the screen of the system. So if we just look at other lines, it doesn't actually matter which key we effectively press. Incidentally, the reason for using open collector outputs is most likely because it doesn't matter if you short some of these together. Even though they're being kind of accessed semi-randomly based on system activity on the address bus, even if two are selected at the same time, because they're only ever pulled high using pull-up resistors, all that's really going to ever happen is you might pull up 2 instead of 1, but it's not going to matter because these won't be trying to sync any real current, and all that's going to happen is the 2 lines coming into this IC will be active at the same time. But that doesn't matter because the system will just think you're pressing 2 keys at the same time, but it won't do any harm to the circuitry. So it's quite a nice aspect of the design here. It just means that although it looks like I've been kind of randomly stabbing away with this jumper lead, I'm not going to do any harm because, as I say, these are open collector output drivers. Okay, so in the next video we'll start investigating this further. We have now got a very nice stable display. We've got rid of that wavering and the distortion and the excessive brightness. It's been running now fairly stably for probably an hour, and nothing's getting hot. It's not doing what it was doing before and starting to break up and make strange noises. So I think we've dealt with the power supply issue, at least for the time being. So we need to start investigating why this system seems unable to get beyond the boot screen.